In my last video, we had ended with a little bit of a quandary and a puzzle with some structures about nitrate. And it turns out that there's a special name for what's going to happen. It's called resonance. And we think about resonance when we have what we're thinking of as equivalent Lewis structures. So let's go back to our problem of nitrate. When we drew nitrate at the end of our last video, we had come to the conclusion that we needed one double bond in the structure, but that it was totally arbitrary which one I picked. So we really had three equivalent structures. And I had said, which one is right? And I had said, yes. And the reason for that is that they are all correct at the same time as they are all wrong. And I know, again, that's unsatisfying, but the way that we think about that in our heads is we think about the real structure as being somewhere in between all of these. And the way that I represent that is I put these double-headed arrows between my structures. And then the brackets in the negative charge are for the fact that it's an ion. And so what we've just drawn are a set of what is called resonance structures for nitrate. Other compounds have resonance structures, and let's talk about what that means and what those rules are. Right? First off, resonance represents the overall delocalization of electrons in the molecule. And we notice with this structure that there's this double bond that just seems to kind of flip around the molecule. It's not in multiple places at once. That bond is itself delocalized. It doesn't belong to one pair of atoms. It doesn't belong here or here or here. It actually belongs everywhere at once. And so another way that we sometimes draw that is like this. We put in these dashed lines to say that these single bonds, which I'm about to highlight in blue, are the permanent bonds. They are localized between those pairs of atoms. This nitrogen and this oxygen really share this blue pair that I'm highlighting. Or this nitrogen and this oxygen really share this blue pair, and so on and so forth. But that black dashed line is that bond that's not really belonging to any one pair of atoms. It's delocalized across. And so what that means is that the real bond lengths, right, there's a single bond, and there's a double bond, and then there's resonance structures. There's somewhere in between. And in this case, it's actually pretty easy for us because we've got one bond shared over three resonance structures, plus the original single bonds. And so the bond order is 4/3 or 1 1/3, right? The bond, it's the number of bonds you split in the numerator divided by the number of structures. And then you add it to permanent bonds. That's how you get bond lengths. Let's try this with just a couple more structures. And again, you're looking for those equivalent structures that you have to have, you have to feel like you make an arbitrary choice. And when you have to make that arbitrary choice, don't make it. Draw the two equivalent structures. Put the arrows between them. So let's try formate, CHO2-. So I hope you got to this point where you had a double bond that you had to put between carbon and oxygen, but you didn't know which one. And so you just drew two equivalent structures, one where you put it in an oxygen at the bottom and one where you put it in an oxygen at the top. You used your double-headed arrow to tell me that there were two structures, and you put brackets around it and a negative sign to show me that it's a charge. Let's try one more. Let's try benzene, C6H6. And one thing that I am going to tell you that's going to be important for helping you when you pause the video and work on this is that the benzene molecule has the carbons in a ring, in a hexagon. So I'm going to set them up like this and let you know that they are connected in a hexagon. And then each of those hydrogens are sticking out. And I'll tell you also that there are two equivalent structures. So C, C, and a couple more. Stop at this point, fill in the hydrogens that I left out, and then do a valence electron count and figure out how many double bonds these structures are missing and try to see where that takes you and where those resonance structures are. But I will tell you that there are two. All right, when you do your double bond check and your octet checks and all that, you should find that there are 3 double bonds to distribute. And in order to make the octets work right and to have carbon only have 5 or 4 bonds each, there should be alternating double bonds. So here, here, and here. But that was an arbitrary choice. I could have just as easily done here, here, and here. Those are my 2 resonance structures for benzene. And what that means is that all 6, right, there's 6 carbon-carbon bonds, are the same length. By the way, that was also true of this. All 3 of the NO bonds equal the same length. If you have bonds in a resonance structure, when I made that arbitrary choice and I had those 3 structures, the bonds that I shared between in the resonance structures are functionally equivalent, which means they all end up being the same length. And they're not quite as long as a single, but not quite as short as a double.